Hello friends, welcome to my lecture on dual of a graph. Let us first define adjacent region. Two regions of a planar multigraph are called adjacent if they have an edge in common. Say for example, the region R1 and R2 are adjacent because they have this edge in common, okay? And then R2 and R3 are adjacent regions because they have this edge in common, this one, okay? And then R3 and R4 are adjacent because they have this edge in common. So, R1 R2 are adjacent regions, R2 R3 are adjacent regions, R3 R4 are adjacent regions. Now, if you take say for example, R1 and R4, okay, R1 R4 do not have any edge in common. So, R1 and R4 are not adjacent regions. Similarly, R2 and R4 are not adjacent regions because they do not have an edge is common. R6, R4, R6, R3, okay, they are also non-adjacent regions. Okay. R5 is not adjacent to R4 or R3. So, the Kuratowski's theorem gives us necessary and sufficient conditions for a graph to be a planar. We have seen that Kuratowski theorem says that a graph is planar if and only if it does not have any subgraph which is homeomorphic to K33 or K5. So, it gives us necessary and sufficient conditions for a graph to be a planar graph. Now, let us see how we consider dual of a, how we get the dual of a given planar graph. Suppose we have a planar graph G, then we can construct another graph G star which is called the dual of G by following these steps. Okay. So, inside each region Fi of graph G, we take a point Pi. Okay. These points Pi are called the vertices of the dual graph G star. We join these points Pi as follows: if two regions Fi and Fj are adjacent, draw a line joining points Pi and Pj that crosses the common edge between Fi and Fj exactly once. If there is more than one edge in which is common between common between Fi and Fj, then draw one line between Pi and Pj for each of the common edge. Let us first see some examples on this before we go to step number 3. Okay, because in step number 3 we have the case where an edge E is lying entirely in one region. So, that will come later. Let us first consider the case where we use step 1 and step 2 to get the dual of a graph. Say for example, let us look at this graph. Okay. Let us find the dual of this graph. So, here we have in this graph we see that there are 6 regions, okay, F1, F2, F3, F4, F5 and the region outside this, that is shown as F6. Okay. Now, what we do to obtain the dual of this graph? Okay, let us take a vertex in each of these regions. Okay. Say inside each region Fi of graph G, take a point Pi. Okay. So, we can take a point P1 here, a point P2 here, a point P3 here, a point P4 here, a point P5 here, okay, and a point P6 here in the region F6. And then the steps 2 says join these points Pi as follows: if two regions Fi and Fj are adjacent, okay, draw a line joining the points Pi and Pj that crosses the common edge between Fi and Fj exactly once. So, F4 and F3 are adjacent regions. So, we join P3 and P4 by an edge which cross this common edge exactly once. Okay. Then F3 and F2 they are adjacent regions. So, we join P3 to P2 by crossing the edge which is common to F3 and F2 exactly once, and then F2 and F1 are adjacent. So, we join F2 to P2 to P1, okay, crossing the edge which is common to F1 and F2 exactly once, and similarly we join P1 to P5 and then P5 to P4 because they are regions adjacent to this one. This P1 and P5 are joined by this edge because F1 and F5 are adjacent regions and F5 and F4 are adjacent regions. So, we join P5 to P4. Now, P6, okay, P6 is adjacent to P3. So, we join P6 to P3, we join P6 to P4, okay. We join P6 to P5, okay, and then we join P6 to P2, P6 to P1, okay. So, because this F6 and F3 are adjacent regions, they are we join P6 to P3, and F6 and F4 are adjacent. So, we join F6 to P6 to P4, okay, and similarly for P6 and P5, P6 and P1, and P6 and P2. So, we get this graph. This graph we can see P6 is joined to P3, P6 is joined to P4, P6 is joined to P5, P6 is joined to P1, P6 is joined to P2, and P1, P2, P3, P4, P5 are joined by these edges. Okay. Now, this graph, so this the graph, okay, shown by dots, okay, is the dual of the given graph. We can draw it like this. The dual graph can be drawn like this. Okay. Okay. We have drawn this graph by taking a point Pi in each region Fi, and the edges of G, here edges of G are shown by solid lines. The edges of G, okay, are shown by solid lines, while the edges of G star are shown by dotted lines. Okay. So, now we draw the dual graph. Okay. You can see we have taken this P6 inside this and P6 is then joined to P3. So, P6 we have brought here. Okay. So, P6 is joined inside this we have P4, P3, P5, P2, P1. Okay. So, we have this. Okay. And then we consider this P6 here, and we join P6 to this is P4, P3, okay, P2, and we have P1 here, and we have P5 here. So, we join P6 to each one of them. Okay. So, that's how we get the dual of the given graph. This is dual of the given graph. Now, so here we considered the case where we did not have this situation, that there is more than one edge common between Fi and Fj. Between Fi and Fj we had just one edge which was common. Now, let us go to more examples. Okay, let us look at this. We have the complete graph of 4 vertices. You see, we have 4 vertices, 1, 2, 3, 4. Each vertex is joined to every other vertex, and therefore, it is complete graph K4. Okay, it is complete graph K4. Now, the complete graph of 4 vertices can be drawn on a plane like this. So, we have what we have done, because it is a planar graph. So, we have drawn it so that no edges of this graph cross each other. Now, we take a vertex. Now, we see there are how many regions? One region is this one region is this one region is here, and one region outside, okay, which is shown by F4. Okay. So, we have we take a point P1 in region F1, we take a point P2 in region F2, we take a point P3 in F3, and we take a point P4 in region F4. Now, F1 and F2 are adjacent regions. So, P1 and P2 are joined by an edge which crosses the common edge between F1 and F2 just exactly once, and then now you see this region F3. Okay. F3 has has an edge common with F2. Okay. This edge common with F2. Okay. And F3 also has an edge common with F1. Okay. So, F3 has more than one edge common, F3 has an edge common with F2. So, we joined P3 to P2, and F3 has one edge common with this edge common with F1. So, P3 joined to P1. Then F4, okay, F4 the region outside, okay, this is shown by F4, we have P4 here. So, P4 is then joined to because this edge, okay, is common between F4 and F3. Okay. So, P4 is joined to P3 and then P4 is joined to P2 because this edge is common between F4 and F2, and then this edge is common between F4 and F1. So, we join P4 to P1. Okay. Right. So, the solid lines graph is the given graph and the dotted lines graph is the dual graph. We can read this graph as follows, this one. Okay. This is the dual graph. You see P3, P2, P4, P1. You see P4 is this one P4. Okay. So, we have P4 here and then we have P3, we have P2, P1. Okay. So, this is P1 and P2 we have here. Okay. Then P3 is joined to P4. Okay. So, this P4, okay. P3 is joined to P1. So, we have this. Okay. Then P3 is joined to P2. Okay. So, we have this and then P1 and P4. Okay. P1 is joined to P4. Okay. So, we have this and then P2 is joined to P4, P2 is joined to P1. Okay. Let us note that number of edges in the complete graph, given complete graph, and the number of edges in the dual graph, they are equal. Okay. Here you can see the number of edges in the given graph, they are 1, 2, 3, 4, 5 and 6. There are 6 edges in the given graph. And how many edges are there in the dual graph? 1, 2, 3, 4, 5, 6. So, dual graph also has 6 edges. So, number of edges in the dual graph is equal to number of edges in the given planar graph. They are equal. Now, let us go to so this is the figure of the dual graph. Now, let us go to dual of each of the following maps. Okay. So, we can so there are one region here, one here, one here and one outside. Okay. So, what we do, we can take a point for each of these regions. So, one here, one here, one here and one outside. Okay. Now, this region and this region, they are adjacent. So, we can join this by this line. Now, this region and this region are adjacent. So, we can join them by this edge, and then this region and this region, they are adjacent. So, we can join like this. Okay. Now, then this region outside, okay, is has a edge common between this region. So, we can join this like this, and then we can join this to this one. Okay. We can join this to this one. Okay. And we have the following graph. See this one, we have this, okay, and then join this to this to this and then this to this. Okay. Now, let us consider this one. In this graph, how many regions are there? One region here F1, okay, this one, this region, and one region here F2, and then one region here F3 is this one, this region, okay, and one region here F4, this one. No, we have F3 only. There are not two regions, there is one region. So, we have this, not F4, F3 only. In F3 region we have two edges, this edge and this edge. In the F3 region we have two edges. Now, you see F1, okay, this region F1, this is adjacent to this region. Okay. So, what we do? We take a vertex here and a vertex here and join them by an edge. Okay. Then this region and this region, they are adjacent. So, we take a vertex here and join like this, and then this region, this one and this one F2, they are adjacent. So, we take a point here, okay, and join like this. Okay. Now, this region is adjacent to this region. Okay. This region is adjacent to this region and they have two common edges. Okay. Two common edges. So, we can join this by this like this, and we can join this to this, okay, yeah, by two edges, because this region and this region F1 and F2 have two common edges. Okay. Now, so we take an edge which crosses here, and we take another edge which crosses here, and then F3 is here. You take a point here. Now, in F3 there are two common edges. This one, it has two edges. Okay. So, what we will do? We take a self loop. Here we see for an edge lying entirely in one region. Okay. Say f k, draw a self loop at point p k of f k intersecting E exactly once. Okay. So, we have to draw a self loop at point p k of f k intersecting E exactly once. So, we can draw a loop here like this, okay, exactly intersecting this edge exactly once, and then we can draw another loop like this. Okay. So, this loop also crosses this edge exactly once. Okay. Now, so this is what we have, this graph. Okay. You can see here this loop crosses this edge exactly once, okay, and this loop crosses this edge exactly once. All right, and then we have joined this to this one, okay, and we have joined okay, this one to this one, this we have joined. This region F3 outside has two edges, okay, lying in F3. So, we have drawn two loops, okay, crossing each edge exactly once. One loop is this one, another loop is this one. Okay. Now, so we also have to join this region with this one, because this region, okay, is isomorphic, is adjacent to this one. Okay. We have this graph now. We have this situation. Okay. So, this is F1, we have drawn it as F1, this is F2, and we have F3, and we have taken a point here, okay, this point, and a point here, this point, okay, and a point here and a point here, and then join them like this. Okay. One point here we have taken. Now, we can, so this we had two self loops here crossing this edge exactly once. Okay. So, we had this one, this, and then another one like this. Okay. Now, we join this to this, because F1 and F3 are adjacent regions. There is a one common edge here, and then F3 is also adjacent to F2. There is a common edge here, this common edge, this one. Okay. So, F3 can be joined to this is P3, this you can call as P1, and then this we can call as P2, we have P3, P4, and here we have P5. Okay. So, yes, and so P3 we have joined to P1, P3 also has to be joined to P2. like this. Okay. So, that is the dual here. We can see this is the dual here. We have joined these 2 points, then you join this to this and join this to this, okay. And then we have these this loop which cross the common edge exactly once, and then we have joined this to this, okay. So, that is the dual. Now, let us see this case, okay. Here we can see here. So, there are how many regions? F1, F2, F3, F4, F5, and we have F6 here, okay. So, we take a point P1 here, P2 here, P3 here, P4 here, P5 here, and P6 here, okay. Then since F1 and F2 are not adjacent regions, okay, we cannot join them by an edge crossing their common edge exactly once, but F6 is has a common edge with F2. So, we can join like this. P6 has a common F6 has a common edge with F3. So, we can join like this, and then similarly we can join this way and then this way, okay, and then we can join like this, okay. Yeah. So, so that is the graph in this case, and we can redraw it like this. So, you see we have let us say this is P1, we have P2 here, P3 here, P4 here, P5 here, and P6 here, okay. So, we have P1, P2, P3, P4, P5 and P6. P6 is joined to each one of them. P6 is joined to P1, it is joined to P2, it is joined to P3, oh no, it is joined to P6 is joined to P3, P6 is joined to P4, P6 is joined to P5. P1, P2 are not joined to each other because between the regions F1 and F2 there is no common edge, they are not adjacent to each other. Okay, so, we have this graph, this one. You see we have yeah. So, this is P1, P2, P3, P4, P5 and this is P6, okay. And yes, we have missed one thing. So, this is P6, let us say, okay. This is F6, we have F1, F2, F3, F4, F5, this is F7 you can say, that one was F6, this is F7, okay. So, I can take this one as P7, okay. This we have to take one here, we have to take. So, we can take that as this one, okay. That one is joined to P7 is now P7, this F7 has a common edge with F1, F2, F3, F4, F5. So, P7 will be joined to P1, it will be joined to P2, it will be joined to P3, it will be joined to P4, it will be joined to P5, okay. So, I should take this as P, okay, I should take this as if I take this as P7, then and join like this, okay. So, P7 is joined to P1, P7 is joined to P2, P7 is joined to P3, P7 is joined to P4, P7 is joined to P5. Now, P7 is not joined to P6 because they do not have a common region, okay. Now, P6, so we have P6 here, P6 is joined to P1, P6 is joined to P2, P6 is joined to P3, P6 is joined to P4, P6 is joined to P5, okay, like this. And we can draw this graph in this manner, you see, okay. This say P1, P2, P3, P4, P5, this P7 and this is P6, okay. So, that is the graph. which is dual of the given graph. Okay. Now, self dual graphs, if a planar graph is isomorphic to its own dual, okay, it is called self dual. Now, let us clear from this example, let us look at this example, this one, okay, this graph we had, okay, we obtained the dual graph like this, okay, and you can see that this graph, dual graph, and this graph, they are the given graph, they are isomorphic. So, this graph, the given graph is called as self dual. Okay. If a planar graph is isomorphic to its own dual, we will call it as self dual. Okay. So, the example 1 was a self dual graph. Now, this was the dual. So, because they are isomorphic, so it is a self dual graph. Since this graph is dual of this graph and they are isomorphic, okay, the given graph is a self dual graph. So, that is the end of my lecture. Thank you very much for your attention.